Welcome back, everybody. So now I want to mention a notion that is very much connected to that of embedding and elementary embedding, but it's simpler, and it's that of substructure. If you remember, in your algebra class, you looked at subspaces for vector spaces. Those are substructures. I don't know if you remember subrings, when you had a ring, it's a smaller ring that is inside. So in general, we're going to generalize that, and we call them a substructure. So here's the definition. So if you have two structures M and N, and they are tau structures, so they are the same vocabulary, use the same symbols, we say that M is a substructure of N. Essentially, pretty much if M is included in N, and everything else behaves the same way in M and in N. Alright? So the constants, the way you interpret the constant symbols in M is the same as the way you interpret the constant symbols in N. The way you interpret the function symbols in M is the same as the way you interpret the function symbols in N, and the same for the relation. So for instance, let's say that we take substructure Z, which is the integers with 0, 1, plus, times, and less than. Okay, and we get R, calligraphic R, is the reals with 0, same structure, plus, times, less than, but now we are talking about the plus and times of the real. So it's not hard to see that Z is a substructure of R, right? It's a subset, and all the operations are the same. We are talking about the same 0, the same 1, plus in the integers it's just a restriction. What this symbol means here is that the restriction of this function plus on the reals to the integers. So that means like this is the plus. These are the same operations, but this one only takes integer values. So this is a restriction of this one just to the integers. And here is the same. This is multiplication for the integers, it's like the one for the reals, but only takes integers. So that's why it's the restriction. And less than on the integers, this one is used to compare integers, but it's the same relation that you use to compare reals, just restricted to the integers. Okay, so that's what that means. So that's what a substructure is. So and one thing that is very important, substructures, these operations, these functions, need to be closed within the substructure. This is implicit in the definition because we have here that Z has to be a structure itself. Well, like the M here in the definition has to be a substructure itself. So to be a substructure, all the functions need to be defined inside you. So you need to be closed under the functions, right? So when you apply the functions inside the substructure, you must stay inside the substructure, right? So in general, if you guys remember, for instance, if you have a group, G is a group, let's say G E star is a group, and then we define a subgroup. So H, usually you say H defined in G is a subgroup if two things, E belongs to H, the identity, and for all H1 and H2 in H, H1 star H2 belongs to H. That's the usual definition in algebra for subgroup, right? So that means that it's closed under the operation. So what we mean here is that if you look at H as a structure itself, with the same operation, what this is saying is that it's actually a structure. E belongs to H, and H is closed under the operation. So when we consider H with this structure, this is itself a structure because it's closed under the operation. So that's the definition of subgroup, and it's using the same relations, right? So this one and this one are the same. So that's what it means to be a substructure. Okay, so you have to be closed. But for us, that's just by saying there is a structure, and all these interpretations need to be the same, just restricted to the smallest guy. So for instance, this would not be the case. For instance, if you take the reals plus with 1 and times, and the reals with 0 and plus, we saw this example before. So the reals, the positive reals are a subset of the reals, right? So R plus is contained inside the reals, but this is not a substructure. Well, for two reasons. One is that this identity element is not the same in both. That's necessary. And also, the operation is not the same in both. So it's not a substructure. Even though it's a subset, it's definitely a subset, but it's not a substructure if it doesn't have the same operations. Okay, so that's what is a substructure. And being a substructure is the same thing as saying that the identity map from M to N is an embedding. Okay, so if you look at this, what this means, identity map doesn't change anything, right? So everything stays the same. So it just says that the interpretations are the same, right? Identity being an embedding is the same thing. This is exactly what that says. Okay, so the identity is an embedding. There is a very interesting kind of substructures which are satisfy more properties than just regular structures, substructures, which are elementary substructures. Okay, so here we say that M is an elementary substructure of N if also you have that M is a subset of N, but also for every well-formed formula phi on any set of variables, if we apply the formulas to some elements of M, the formula is true in M if and only if it's true in N. Okay? So I guess here we can think of this is our N, and here is our M, and these points M1, M2, and M3, and M4 belong to M, and if they satisfy the formula phi, then as interpreted inside M, they also satisfy it in N, and it actually is if and only if. So actually one thing to comment, in the case of a substructure, since we have that identity is an embedding, remember embeddings preserve not only constant functions and relation symbols, but embedding actually preserve all quantifier free formulas. Okay? So this is true for just substructures when you have quantifier free formulas. In an elementary embedding, this is true for all formulas, not just quantifier free. Okay? So this is for quantifier free formulas. Here is all formulas. So these are pretty nice, these elementary substructures, because like everything, any first order statement you can say about the smaller one is true in the bigger one and vice versa. So let's look at some examples. So the integers and the rationals with plus, well, they are not even elementary equivalent, right? So if you're an elementary substructure, you satisfy in particular the same sentences, right? Because I mean, just consider the case when we have no free variables, you should satisfy the same sentences, and these two we know already they are not elementary equivalents, right? So we know that's a symbol for elementary equivalence. So these two are not elementary equivalents. We saw that before. There's a sentence you can write that is true in one and not true in the other. So there is no way they are an elementary substructure. So this is 2c. 2c here I mean the even integers. So this way here I mean even positive and negative, because it's 2 times the integers, so 2 multiplied by all the integers. So actually that is still a group. So because if you add 2 even integers, you stay with an even integer. So it's actually a subgroup, and actually it's isomorphic. So we do have that the even integers with plus is a group that is isomorphic to the integers with plus, and then the isomorphism is just multiplied by 2. Take an integer multiplied by 2, you go from all the integers to the even integers. So it's an isomorphism, and that means they are in particular elementary equivalent. So they satisfy all the same sentences. So actually we do have that 2z plus, so that means that they are isomorphic, and also that implies 2z plus elementary equivalent. Okay, so that means they satisfy the same sentences. Okay, but then elementary substructure is just more than satisfying the same sentences. You need to satisfy all the same formulas with the elements from the smaller one. In this case, the more smaller one is the even one. And this is not the case, right? So for instance, if you consider the formula phi of x be the formula that exists a y star y equals x, or let's say there is no y such that y star y equals x, we get that 2z, this is true in 2z, with plus of the element 2. There is no element, it cannot be divided in, it's not the sum of two even integers, 2, but in Z alone with the same element, this is not true, because 2 can be considered written as a sum of two integers, 1 plus 1. So and to have elementary substructure, we need to have this for all m that belong to the smaller one. So in this case, we're using 2 that belongs to 2z, and this one is true, one is true, and the other one is not true. Okay, so that's why it's not an elementary substructure, even though it's an elementary equivalent structure. Okay, so here's an example. We saw before this z plus z. We said that this is an elementary embedding, but actually it's an elementary substructure because it's a subset. So actually it has more, it's a stronger statement that it's an elementary substructure. Remember, z plus c here means the two chains, one on top of the one after the other, as we saw in the videos last week. So we're gonna have tools to prove this later in the course. And here's another one that is very interesting. So the rationals with plus, the group of the rationals with plus, is an elementary substructure of the reals with plus. And that's also an elementary substructure of the complex numbers with plus. Now this is a more difficult one. Yes, we're gonna see later what we do with this one. But this is very interesting. So with plus, they satisfy all the same formulas. And the ordering, this is less surprising, I guess. The ordering of the rationals and the ordering of the reals, those are also an elementary substructure. So we need to start developing tools to prove all these things that we are claiming. And that's going to come next week. See you guys later.